So let's talk about the magnetic force that exists between two parallel conductors. And this happens a lot in stranded wire and stuff like that. So this really does happen out there in the real world. But first, let's review what we did last time. Remember that we used the Biot-Savart law, which is this very awkward thing that says that really tells us where magnetic field comes from. It says that the magnetic field comes from, well, we have this constant of nature, mu naught over 4 pi. And then we multiply that by the current. But the current, we're going to say in all the problems we're going to do, the current's going to stay constant. So it's just a constant. And then we are going to integrate, and we're going to say, well, it depends on how long the wire is, which we represent with ds, how much current, how that current is distributed in space. That's what the ds represents. We cross it with r hat. This gives us the direction of the magnetic field. And then, depending on how far away from that current is our location in space, because it decreases by the square of the distance. So this is a difficult equation to memorize until you start thinking about all the little pieces. Okay, you've got current. What is the cause of magnetic field? It's current. And really it depends on, well, we always have a constant of nature, right, in these basic laws, these field laws, what gives us gravitational fields and electric fields, now magnetic fields. We need to define the direction of it. This is the length of this ds represents the length of our conductor, and this represents how far away we are. So it all kind of makes sense when you break it down piece by piece. So don't be too afraid of this thing. Now we used this to figure out what the magnetic field was for a really long straight wire. For a really long straight wire, and we want to know what is the magnetic field at some point off the wire. And we said that magnetic field was equal to mu naught I over 2 pi a. And this expression for the magnetic field came from the Biot-Savart law, where a is the perpendicular distance really from the wire to our location in space. Now here's one thing we didn't have time to get to, so I want to do that now before we get to the main topic today. And that is that this tells us the magnitude of the strength of the magnetic field, but the direction of it, well, we did kind of talk about that. We get the direction. You can always think of the what's the direction of the magnetic field using the Biot-Savart law. Okay, it's not that bad. You just have to go ds cross r hat, but you have to know what ds and r hat are, okay, for this problem. Well, let me zoom in because I wrote too small. Okay, so there's my, so let's say here's my current, right? There's my current I running through this long wire. And so I'm going to pick a little ds right here. And so ds is to the right. Now what's r hat? R hat is from the little differential or infinitesimal line segment that I'm looking at, my ds, and then to my location in space. So it's the direction from ds to the point in space, right, like that. And so the direction of this B field right here is ds cross r hat. And so if you take your right hand, well, now I got to zoom out again because my right hand will look monstrous. Okay, so you have ds cross over to r hat, so my thumb points out. So this points out of the board. Okay, now what I'm going to do is I'm going to use this same idea, what I just did, but I'm going to look at this wire in cross-section, okay? Or what I'm going to do is I'm going to put my eyeball over here, okay? There's my eyeball. Okay, so I'm going to look at it from this perspective. Right through his head. All right. So if that's true, then the wire looks like this, doesn't it? Okay, and we can say that ds is coming out of the board. Okay, so this represents my ds vector, and here's my location in space. So here's r hat. Now, can you use the right-hand rule, everybody? Try it. Yes? Oh, very good. DS, your finger comes out. Oh, look at that. That's kind of scary. DS, and then I flop my fingers over to R hat. And my thumb sort of points that way. So my magnetic field is going to look like this. But what if A was over here? Okay. Now R hat points towards A, and you just go ds cross R hat, it looks like this. There's my magnetic field. Or what if my location in space was over here? It would look like this. Now what do we do when we draw field lines? We connect all these arrows together, right? Remember we did this with electric fields. And what it does, zoom in, is it creates a circle. It creates a circle. And so this magnetic field line, and it's kind of hard in this picture to imagine what's going on, but I've got a wire that's coming straight out, with current coming straight out of the board. Let me draw it in some perspective here. If I've got a wire that looks like this, and it's got current going through it, and I go a distance A out from the wire, if I go ds cross R hat, it's going to come out of the paper here. It's going to make a circle like this. This is the magnetic field line, and it comes. And the way you just put arrows on it. Now I always, to show the perspective of it, when I draw these things, and you have to become skilled at drawing in 3 dimensions, and it's not easy to do. Okay, but notice I drew a little break in the field line to show that it's behind the wire, because here's the wire, here's the current, and so it wraps around like that. So I usually try to draw a little break to show, and then maybe you can make this a little darker to show that it's in front of the wire and then back. So there's your B, and it's a circle. So if you have a long straight wire, the magnetic field lines make concentric circles around the wire. Now here's the magnitude of it. Now what if I go farther out? Well, A is greater, so the magnetic field is weaker. But when you do the ds cross R hat, you still get, for all the points that are A away, you still get a circle. Okay, and the closer you get to the wire, the stronger the magnetic field lines, and we show that by drawing the field lines closer together. But you just have a series of concentric circles representing the magnetic field lines. So this is pretty cool. And also there is a principle here we're going to get to later, but magnetic field lines always make closed loops like this. Now, that wasn't true with electric fields or gravitational fields, right? Electric fields had a starting place, which was positive charge, and they had an ending place, which was negative charge, right? They went from the positive to the negative. They started somewhere, then they terminated somewhere. Not true with magnetic fields. Because magnetic fields obey this Biot-Savart law, they always make circles. Now this is why you can't break a magnet in half and just have a north pole. When you break a magnet in half, you just create another south pole and another north pole, right? You just create two separate magnets. Because the field lines, there are, have to make loops. Okay, so anyway, this is kind of finishing up what should have been part of the last lecture, but we just ran out of time. All right, so now here's what we've got. We've got, one last thing. There is a right-hand rule for figuring out the direction of magnetic field lines. And remember, it all comes from the Biot-Savart law, okay? And that's a right-hand rule, right? Because you've got a cross product, ds cross r hat. And by the way, if you can always use the Biot-Savart law, that ds cross r hat, you can always use that to figure out the direction of the magnetic field line. But there's this easier way for long straight wires. And we deal with long straight wires a lot. So this is useful. So zoom all the way out. Because I need to use my hand here. Here's what you do, everybody. And even those of you watching at home, okay, take your right hand, okay, and grab the wire with your thumb in the direction of the current, that the current's flowing in. So if the current is going up the wire like this, in your imagination, well, let me use the pencil, because this will be better. So here's my pencil, and let's let the pencil represent the direction of the current. What you do is you grab the wire with your right hand with your thumb in the direction of the current. Your fingers curl in the direction of the magnetic field. Everybody. All right, do you see how my fingers are going like this? Yes? All right. Same. Look at this. Look at my drawing. If I go behind that wire and then in front of the wire, and that's the direction, that curling of the magnetic field due to the long straight wire with current in it. All right. So let's move on to today's main topic. What if I've got two wires that are parallel to each other with current flowing through them? So here's a wire and here's a wire. Now these two wires are connected to, these wires are connected to voltage sources, and so they have currents flowing through them. So let's have this be wire 1, and this will be wire 2. And so this has current going up like this, and this has current flowing up like this. Now, here's the deal. We can combine the two ideas that we've already developed. This wire has current, and anytime you have a current, it creates a magnetic field. But this wire, and this wire feels, wire 2 feels the magnetic field due to the current in wire 1. And when you have a wire in the presence of a magnetic field, that wire feels a force. So wire 2 feels a force due to the magnetic field created by wire 1. But wire 1 feels a force due to the magnetic field created by wire 2. Now, Newton's third law will tell us, says to us, those forces have to be equal and opposite. And we're going to find that, yeah, they are going to be equal and opposite. So this is going to be consistent with what Newton told us. So here's what I'm going to do. I'm going to take a look at the magnetic field due to the long straight wire and current 1, I1. I'm going to call this I1. Well, I'm going to grab wire 1 with my right hand. Okay, my gigantic right hand. And it goes, so when I get over there, it's going to, when I get over here, it comes out of the paper here, and it comes across and goes down, and goes into the paper right here. So all along here is a magnetic field that's down. See, Philip, this is for you. So along wire 2 is a magnetic field due to the current in wire 1. Now what is the magnitude of that magnetic field? I'll call this B1. B1 is the magnetic field due to current 1 at the location of wire 2. And I'm going to call this a distance, what do we call it? A. I'm just going to say that they're A apart, the two wires. Well, it's equal to mu naught I, but which I is causing this magnetic field? I1 or I2? I1 over, well, this is A, it's over 2 pi A, where A is the distance between the two wires. Okay, well, now I can use my Phil Crosby equation. The force on wire 2 is equal to I, but I2 now, this is I2. I2, IL. Now we're just going to give these a length of L. Let's say they're parallel, but they have the same length. IL, and then it's L cross B. Now we got to do this L cross B thing, okay, to get the direction of the force. Okay, now remember Phil Crosby, okay. We've got you go in the direction of L, you know, the current's flowing like this, and then B is into the board, so my thumb is going to point to the left.
Where you have F sub 2, is that the force on 2?
The force on 2 due to the current on 1. It's the force on wire 2. That's a good question. So this is F2 right here. Now, what is its magnitude? Well, it's I2. Now, by the way, notice that the displacement of the moving charge, L, is perpendicular to B. You know, this is like this is straight down, so that's 90 degrees. So we don't have to really worry about the cross product. I mean, its sine of 90 degrees is 1. So I2, L, and now what is B? Mu naught I1 over 2 pi A. And so now that looks kind of ugly. Let's put it all together. F2 is equal to mu naught. Let's go I1, I2. And I'm going to put the L over 2 pi A times L. Now what direction is it? It's in the, well, let's squeeze it in here. It's in the negative I hat direction based on our cross product. Now let's look at wire 1. Well, because wire 1 is going to feel a force, isn't it? Now, due to the magnetic field of I2. So here's I2. This current is coming up. And because of that, it creates a magnetic field. And we want to know what is the magnetic field at the location of wire 1. Okay, everybody take your right hand in your imagination. Take your right hand and grab wire 2 and tell me what is the direction of the magnetic field at the location of wire 1. Is it out of the board or into the board? Okay, grab it with your right hand. Your thumb is in the direction of the current, and you got to curl your fingers. Now I'm going to use the pencil here to represent. And look, if I grab this with my right hand, my fingers are coming out. So that means that the magnetic field at this location is out. Now this is B2. So let me, hold on a second, where'd my eraser go? Let me erase this guy. Leave a little room off to the side here. Well, what is this magnetic field right here? What's its value? We're going to call that B2. B2 is the magnetic field due to current 2. Well, it's mu naught I2 over 2 pi A. And now we know its direction. It's out of the board. So we've got a current now, I1, in the presence of a magnetic field, B2, and therefore we're going to get a force. So we're going to call this F1, the force on wire 1, is equal to I1 times L cross B2. Okay? Well, let's do L cross B2. So L, that is the displacement of the charge moving through the wire, goes up the wire like this. So there's L, and I'm going to take my right hand and fold it over towards B. Well, B2 is coming out. So if I fold my fingers up, oh, my thumb now points to the right. So this is F1 on the wire. And so F1 is equal to I1 times L. Now, it's a 90-degree angle between L and B2. So it's just L times B2, but B2 is mu naught I2 over 2 pi A. So let's rearrange this. Oh, in what direction? It's in the I hat direction. So F1 is equal to mu naught I1 I2 over 2 pi A all times L in the I hat direction. So you can see that the force on these parallel wires are equal to each other. Look, this force and this force are equal, but this was to the right and this one's to the left. So Newton's third law is happy. And by the way, this is a really good thing. It's a good thing that if you've got two wires that are parallel to each other, that there is a force between them and that force is attractive. Why is that a good thing? See, how many of you, oh, well, Ned is not here today, but, the people who wire up robots are very happy about this because we use this stuff called stranded wire. Oh, yeah, there you are. Stranded wire. What is stranded wire? It's a bunch of little wires like this, right? All in the same cable. Well, these individual wires each have current in them. They each create their own magnetic field. And what do? They actually attract each other. So these currents that are all parallel to each other actually hold each other together when there's current flowing through them. Now that's a good thing. Because what if the wires were in the opposite direction? This is a good way to memorize this, because on multiple choice on the AP test, they'll ask you, do currents that are parallel, are they, well, anti-parallel means they're going in opposite direction. They're parallel but in opposite directions. I think it's going to be easy to see that those wires are going to push each other apart. So let me zoom in a little bit so you can see where I'm at. Okay. Suppose I've got a wire 1 and wire 2, but this current is going like this. There's I1, but this current's going down like this. Now, what's going to happen? Well, and we don't have to go through all those calculations again. Let's just look at the magnetic field due to I1. Grab the wire in your imagination. Here's I1 represented by the pencil here. I'm going to grab it. My fingers go down. So here's the magnetic field. There's B1. Now, the displacement here is down. So when I go L cross B, my force is to the right. Now, on this one, when I grab this wire, B2, let me zoom all the way out so you can see my hands. When I grab this wire, my fingers go into the board for this one. And so when I go, I or L cross B for this, the force is that way. Okay, so if the currents are in opposite directions, the wires will push themselves apart. Okay, and so that's what's going on with wires that are parallel conductors. Okay, here's the whole thing. Remember that it all comes from Biot-Savart. From Biot-Savart, you get, for long straight wires, you can derive this equation. If you have two parallel wires, they interact. There's a magnetic interaction between them. Wire 1 creates a magnetic field that interacts with the current 2. Tries to pull it to the left. Current 2 creates a magnetic field that interacts with current 1. Tries to pull it to the right. Equal and opposite forces. And here's the equation. Now, by the way, one last thing. Quite often they will take this equation and divide both sides by L. And so what you get, like F, let's just deal with the magnitude. The force per unit length is equal to mu naught I1 I2 over 2 pi A. They'll just say, okay, the force per unit length is 30 newtons per meter.
They call it force density?
And no, they don't, but that would be a good name for it. Force density. It's kind of a linear density for force, but I'm not sure you can have a density with a... Oh, yeah, you can. Yeah, you can call it force density, sure. Why not? But it does represent how much force you have per unit length, so yeah. No, you're right. Okay, that's it.